Hi. In this video, we're going to continue our discussion of vector spaces, introducing ideas of basis, dimension, and leading into a discussion in a subsequent video on how these ideas relate to the four fundamental vector spaces associated with a matrix. At the end of this unit, you should be able to explain what a basis of a vector space is, how it relates to dimension, be able to find a basis for the row space of a matrix, being able to find a basis for the column space of a matrix, be able to find the basis for the null space of a matrix, as well as be able to explain the relationship between the four fundamental subspaces of a matrix. In the first part of this unit, we're going to introduce the ideas of linear independence, dimension, and basis. So let's begin. Let's start a discussion with a discussion of ideas of linear dependence and independence. These are ideas we have mentioned in passing already, but we haven't really gone into very formally. When we have a set of vectors, a collection of vectors, if at least one vector in that set can be written as a linear combination of the others, we say that the set is linearly dependent. All that matters is that one vector in the set can be written as a linear combination of the others. It doesn't matter how many others there are. If at least one can be written as a linear combination, the set is linearly dependent. If no vectors from the set can be written as linear combinations of the other, we say the set is linearly independent. Some examples shown here. The set of two vectors from R3, 1, 0, negative 1, and 1, 0, 1, and 1, 0, negative 1. This set is linearly independent because neither of these are scalar multiples of each other. And that's the only way we can write linear combinations when we only have two vectors. On the other hand, this set of three vectors where we've added an additional vector of 2, 0, 2 is a linearly dependent set because that third vector we added in is a scalar multiple of 1, 0, 1, a linear combination of the other vectors. The set T, where we've added a different vector, 3, 0, 1, is also a linearly dependent set because we can express 3, 0, 1 as a sum of 2 times 1, 0, 1 plus 1, 0, minus 1. And again, we can represent 1 as a linear combination of the others. If we had added a third vector that was not able to be written as a linear combination, let's say, for example, we defined the set 1, 0, 1, 1, 0, negative 1, and the third vector we added was 1, 0, 1, 0, this would be a linearly independent set because clearly this third vector cannot be written as a linear combination of the first two. So that just defines these ideas. What does it mean to be linearly dependent or independent? We've also discussed how we can consider the rows and columns of a matrix to be vectors. And that means that in the context of a matrix, we can discuss whether the rows are linearly dependent or independent, and the columns are linearly dependent or independent. If we look at these three examples here, in matrix A, row 2 is 2 times row 1, and row 3 is 3 times row 1. So clearly the rows are linearly dependent, and the columns are all the same, so the columns are also linearly dependent. In B, we have an echelon form, an upper triangular form, and upper triangular forms tend, especially when we have all zeros on the all non-zeros on the diagonal like this, are linearly independent because we can if we think about any linear combination, any scalar multiple of this first row would have to have a non-zero entry in this first element, which can't be true. Any linear combination of the second one only would have to have a non-zero entry here, and so on. We have 3 linearly independent rows. The same argument can be made for the columns. Any linear combination of this, or any scalar multiple of this third column, would have to have a non-zero entry in these other two. If we're not allowed to take non-zero combinations of this, any multiple of this would have to have a non-zero entry here. So both the columns and rows are linearly independent. For square matrices, we are going to find this to be true. Either the rows and columns are both linearly dependent, or they are both linearly independent. For non-square matrices, we have to really consider things separately. In this case, the rows of C are linearly independent for the same reason as we discussed in B. But the columns of C are linearly dependent. You can actually observe that this last column is the sum of the first 3 columns. And so we have a case where the rows are linearly independent, but the columns are linearly dependent. We will later on in this unit see the deeper relationship between the linear dependence and independence of the rows and columns of a matrix. Okay. Now that we've introduced the idea of linear independence, I'd like to introduce the idea of the dimension of a linear span. Remember that a linear span is a set of, the linear span of a set of vectors is a vector space that is defined as the set of all possible linear combinations of those vectors. And we call that set that we start with a spanning set, a set that we use to define a vector space. If a spanning set is linearly dependent, that is, some of the vectors in that set are linear combinations of others, we can remove any of those linearly dependent vectors without changing the span. Why is this? Well, because when we define a span, define a vector space as the set of all possible linear combinations, any of the linearly dependent vectors in that set will be reconstructed in that process of defining the vector space. So if we go back to those 3 sets of vectors that we saw before, where 2 of the vectors are shared in all of them, but we've added a linearly dependent vector in S and T compared to R, the linear span of all of these is the same. Right? We can remove this vector 2, 0, 2, we can remove this vector 3, 0, 1, and we get the same linear span. Right? Because the span is can be defined as the linear combination of just these 2 linearly independent vectors. So we see that we can remove these 2 vectors and get the same span. The span is defined as a linear set of all linear combinations of these 2. What we mean by the dimension of a linear span is exactly this number, the number of linearly independent vectors in a spanning set. So the dimension of this vector space that can be defined as either the span of R or of S or of T is all 2. 2 linearly independent vectors. What does dimension mean geometrically? Right? It's the number of linearly independent vectors in a spanning set. It tells us how many vectors we need to generate the space. What's the number of vectors in the set that we're going to use to create the vector space? So let's think about this geometrically. if we start with a vector space of, let's say, with one vector, and we generate a vector space from only one vector, all linear combinations of that one, that gives us a line through the origin. If we start with two vectors, we use two vectors that are linearly independent to generate all linear combinations, we'll end up with a plane. Right? And so a vector space of dimension 1 is a line, a vector space of dimension 2 is a plane. Right? These ideas extend in higher dimensions to higher dimensionality equivalents of a plane, flat geometric objects, but our visualization of those kind of breaks down when we go past 3 dimensions. And we can also move in the other direction by 1 unit and ask, what does it mean to be a vector space of dimension 0? Well, that's a point, in fact, the point of the origin, and this is the case where we have no generating vectors. Every vector space has to include the origin, so if we don't give anything else, that's the only thing we have. So these ideas that we've discussed before, vector spaces being flat geometric objects, points, lines, planes, and the higher dimensionality extensions of those ideas are captured in this concept of dimension. How many vectors do we need to generate the space? Okay. If the dimension of a vector space is a number of linearly independent vectors in a spanning set, we can say a couple of things just knowing this. First of all, if a spanning set has more vectors than the dimension, some of them have to be linearly dependent. If we know that a vector space is dimension 2 and we're given a set of vectors from that space that has 3 elements, we know there must be linear dependence there. There must be redundant vectors that don't provide any additional information about the space. We could get rid of those and still be able to generate the space equally well. We can also say that if a set has fewer vectors than the dimension, it can't be a spanning set for that space. So if we have a vector space that's a plane and we only have one vector, we cannot generate that plane from that one vector. We need to have 2 vectors and they need to have to be linearly independent. So any set that is a spanning set but is linearly independent will have the same number of elements. It will have the number of elements equal to the dimension, and we call that a basis. Very simple term for really a very simple concept. It is just a linearly independent set that is able to generate the vector space, a linearly independent spanning set. Simple idea, but very, very important to a lot of what we do in linear algebra. Okay. Just to sort of recap what we've discussed so far, a basis for a vector space must be a set of linearly independent vectors. This accounts for there not being any more vectors than are necessary. And it must be a spanning set. There can't be fewer vectors than we need to generate exactly the right number of vectors, exactly the smallest number of vectors that are able to completely describe a vector space. Very important to note that a basis is not unique. Any linearly independent spanning set is a basis. And for any vector space, there is an infinite number of bases that we can define. So any single vector on a line through the origin is a basis for that line. And of course, there's an infinite number of such vectors. any pair of linearly independent vectors that sit on a plane through the origin is a basis for that plane. There's an infinite number of those pairs. As we move on, we will see that there are ways to define certain bases that have particular properties that are easier to work with. But for now, let's think of just the very general definition of a basis being any linearly independent spanning set. The dimension of the vector space is the number of vectors in a basis. Every basis for a vector space has the same number of vectors. It defines the geometry of the space, a line, a plane, or so on, and it is just a single constant number. A vector space has a dimension that does not change, right? Unlike the basis, where there are many, many different possible bases for a vector space. So far, we've really just defined these ideas. What are some of the outstanding questions? Given a set of vectors that span a vector space, how do we find the dimension and a basis? Underlying that problem, how do we know if a set of vectors is linearly independent or linearly dependent? If a set is linearly dependent, how do we know which ones are linearly independent and which vectors aren't? Which vectors can we safely remove without changing the span? If we could answer these two questions, then we would be able to define a basis. We could remove vectors from the set until we had a linearly independent set. So how can we address some of these ideas? One approach is focused on an idea that we've already discussed in detail, elimination, and relating this back to the row space of a matrix. Remember that the row space of a matrix is simply the linear span of the vectors corresponding to each row. We take a vector and we define a vector. So we take a matrix and we define a vector associated with each row of this matrix. We define a set of those vectors, and the row space is just the span of all of those. Right? Now, during elimination, forward elimination, back substitution, really all of the processes of Gaussian elimination, what we fundamentally are doing is taking linear combinations of rows. We're adding a scalar multiple of one row to another, subtracting a scalar multiple of one row to another, multiplying a row by a scalar. These are all acts of taking linear combinations. Right? So elimination is a process of taking linear combinations of the rows of a matrix. It's also fairly easy to show that if a set of vectors can be linearly combined using non-zero coefficients to give the zero vector, that is, if we can find a set of non-zero A, B, and C so that we add together three vectors and they give us the zero vector, then they must be linearly independent. Why? Linearly dependent. Why? Because if we can do this, we can rearrange this expression to write, for example, W as a linear combination of U and V. And this simply requires that C was not zero. So if we can write something like this with non-zero coefficients, we know that the set has to be linearly dependent. What does this mean? This means that when we take linear combinations of rows, we can only get a zero row appear if the rows were linearly dependent. Elimination is just taking linear combinations, and the only way linear combinations can generate a zero vector is if the set was linearly dependent to begin with. Okay. Also, just by how we define a vector space as a linear span, if we take linear combinations of vectors from a vector space, they have to also be in the vector space. And this means that as we go through the process of elimination, we're not changing the row space in any way. We are taking linear combinations of the rows. Every vector we generate, every new row we generate is in the same row space. The only things that disappear when we generate 0 rows are linear dependent vectors. So 0 rows will only result if we had linear dependence, and every matrix generated through the process of elimination has the same row space. So if we go from A to an echelon form U to a reduced row echelon form R, all of these matrices have the same row space. These two ideas taken together, give us a method to compute the basis for the row space and to determine its dimension. Quite simply, the non-zero rows of any echelon form of a matrix are a basis for its row space. The act of going through elimination has created zeros where there were linear dependence, and everything that's left when we get to an echelon form must be linearly independent. It also must span the same row space, and so those rows are a basis. The dimension is simply the number of vectors in a basis, so we count the non-zero rows, and that gives us the dimension of a basis. We can apply this approach to give us this method for defining a basis for the row space of a matrix to find a basis for any set of vectors from a spanning set simply by using the same approach. We create a matrix whose rows are the spanning set. We start with some set of vectors that we don't know if they're linearly dependent or not. But we know that they span some vector space. We set those up as the rows of a matrix, and we carry through Gaussian elimination, either to U or all the way to R, depending on the details of the problem. During that process, we may generate 0 rows, and so if we started maybe with M vectors, we may be left with only R non-zero rows. These non-zero rows are a basis, and the dimension of the span of this set is the number of non-zero elements. This we call the row space algorithm. Let's work through a couple of examples. First of all, a straightforward one, computing the basis and dimension for the row space of a matrix. We were given a matrix A here. This is a 4 by 4 matrix. We want to find the dimension of the row space and a basis for it. We simply apply elimination. As always, start with a pivot, eliminate downwards. I'm not going to walk through all of these steps in detail. You can work through the algebra of it, or the arithmetic of it yourself, but we walk through this, eliminate our first row, move over to our next pivot. It's a 0, but there's non-zero entries below, so we need to swap rows. Now we have a pivot, eliminate downwards to 0 out. We then find when we move over and down, we have a 0 that has zeros below it, so we can move over. Next pivot, eliminate downwards, and we're left with a upper triangular or echelon form. There are 1, 2, 3 non-zero rows, so the dimension of the row space is 3. A basis for the row space is found simply by taking these 3 rows, 1, 1, 1, 1, 0, 1, 1, 1, and 0, 0, 0, 1. Problem solved. Let's look at another example using the row space algorithm to find the basis of a dimension of an arbitrary spanning set. We're given some set of 3 vectors, and we would like to find the dimension and the basis of their span. What do? We take these vectors and we arrange them as rows. Important, we're using the row space algorithm. It doesn't matter how our original vectors are oriented. We need to place them in rows. So 1, 2, 1, 2, 1, minus 1, and 0, 2, 2. And then, again, carry through elimination. First zeroing out with our first pivot, then moving down and over to zero out below the next one, and then recognizing that we are at a echelon form. We could have stopped here, and it would be perfectly fine to stop here and say we have 1, 2 non-zero rows in an echelon form. The dimension of the row space is 2, and a basis would be defined by 1, 2, 1 for the first row, and 0, minus 3 for the second vector. We very often don't stop in an echelon form, but rather carry on to a reduced row echelon form, scaling this row and eliminating upwards to give us a reduced row echelon form, and we can take the same analysis. 2 non-zero rows, back substitution doesn't introduce 0 rows, and basis vectors given by these 2 non-zero rows, which I've highlighted here. The reason that we often do this may be apparent just looking at this basis compared to this basis. The vectors of this basis are simpler. They both have zeros in them and only ones. Fewer complicated, less complicated vectors than the original one here. This is a recurring idea in the row space algorithm that if we take things all the way to a reduced row echelon form, we can often find not only a basis, but a fairly simple basis, a basis that has vectors that have a lot of zeros in them. Okay, that's one way to find a basis. Let's think about another. We've discussed the column picture of a linear system as well. In the column picture, x represents the coefficients needed to express the right-hand side as a linear combinations of the columns of a matrix. That is, ax equals b, representing A as a set of columns, can be rewritten as x1 times c1 plus x2 plus c2 and so on, and this sum gives our right-hand side. We've discussed how the column space of A is the linear span of these columns and represents the set of all possible right-hand sides with a solution. There will be a solution if and only if B is in the column space. We also know that there will only be a unique solution if the columns of A are linearly independent. If there's linear dependence in the columns, there will be free variables, there will be more than one way to write a linear combination of a single right-hand side. These ideas lead us to the statement that the columns of A will be linearly independent if and only if the null space of A is the 0 vector only. We know that if the right-hand side is a 0, there has to be a solution. If there's more than one solution, then there isn't a unique solution. The columns aren't linearly independent. If there's when there's no free variables, when every column contains a pivot, the columns of A are linearly independent. How can we use this? Well, let's take a little bit of time, first of all, to think about how elimination again relates to the column space. Why are we going to start with elimination? Well, it's given us so much. It's given us a general way to solve a linear system. It's given us a way to compute a matrix inverse, the LU decomposition. We've seen how we can use it to find a basis of the row space. Let's see if it can tell us something about the column space also. One important thing to note is that because elimination is taking linear combinations of rows, it mixes up columns, right? That is, it scrambles the elements within a column. The column space is not preserved during elimination, unlike the row space. If we go from A to U to R, these should say column space here. The column space of A does not equal the column space of U. The column space of A does not equal the column space of R. Actually, the column space of U and R usually are the same, but that's a fact for another discussion. So the column space is not preserved during elimination. Important thing to remember. However, elimination is driven by the pivots. Every decision we make in what step to take in elimination is based on looking at pivots. Columns with free variables that don't have pivots have absolutely no impact on the elimination steps. If we started with a matrix and we removed the columns with free variables, we would take exactly the same elimination steps to find an echelon or reduced row echelon form. If we were to do this, remove free variables in this way, removing free variables can't introduce a 0 row, right? Because they don't have pivots, they can't include the first non-zero entry in a row, which means removing a free variable column can't make a row become 0. It's 0 rows that lead to, in a coefficient matrix, that lead to there not being a solution. So removing a free variable column can't change the existence of a solution for a given right-hand side. It can't change the column space, that is. It can't change which right-hand sides have solutions and which don't. However, removal of a free variable column does change the number of solutions. You get rid of a free variable column, it changes the dimensionality of the null space, if you will, whether it's a line, a plane, or so on, and that's related to the number of solutions we have in a general solution for any right-hand side. A unique solution exists only when there's no free variables, and that again is the case where we have linearly independent columns. These three ideas, that elimination is driven by pivots, so maybe we can remove the columns with free variables. The idea that removing a column of a free variable column preserves the column space, and that when we have no free variable columns, we will have linearly independent columns, gives us everything we need for a method to compute a basis. Right? The order of those slides was off a little bit. number of pivots in any, oh, sorry, it wasn't, I did want to actually, sorry about that, I forgot. I wanted to mention this one thing. I wanted to take a moment to emphasize what we really mean here, in that we are missing, that we can eliminate free variable columns and not change anything. Right? We might start off with the system shown here. AX equals B, a 3x4 coefficient matrix with this right-hand side. And if we were to try to solve for the general solution, the way we considered in Unit 6, start with the augmented matrix here. So we have our right-hand side column and our coefficient block, and carry out elimination. Right? Eliminate downwards with our first pivot to zero out the first column, and then move over. Up, we have a 0 column. That tells us that, so then we move over to the next pivot, eliminate downwards, and actually already at this point we have a echelon form. This is U. Right? But if we wanted to solve this system, we would continue all the way through, scale this row to give us a 1 here, eliminate upwards to 0 out this column, then move over to our next pivot, and we note that that is already a 1, so we're done. This is our R. Actually, remember that these are augmented matrices, so this is actually the first block is U and the first block is R. And again, using the tools from Unit 6, we can directly read a solution out of this. The particular solution, we first of all identify free variable columns. The free variable columns are 2 and 4. These two columns are free variables. Our particular solution, we set the free variables to be 0, and we read off a 4 and a negative 2 from the last column. For our null space vectors, we set one free variable to 1, the other to 0, and read off the negative 2 and 0 for the first one. And for the second one, we set our, sorry, this should be apologies here. This free variable should be a 1. And we would read off the entries in the next piece as -1, -1 for this null vector. For the, what do we mean when we say we can eliminate vectors? The free variable columns without changing anything. Well, we identified that the free variable columns were columns 2 and column 4. So let's think about taking these two columns and simply deleting them. That would give us this matrix. It has the same first column, has the third column, and has the right-hand side. If we look for the solution of this system, do the same thing, Gaussian elimination downward to 0 out the first column, move over to our next pivot, eliminate downward to eliminate the next one, scale rows, eliminate upward to our reduced row echelon form. Simpler because we have fewer columns here. And what are we left with? We now have no free variables, so we only have a particular solution, and that particular solution is given by the last column. If we compare this back to our original set, how does this differ? Not very much. We have deleted the free variables, so we no longer have any null space. We've deleted the free variables, and so we ignore these 0 pieces from this. but otherwise the solution is unchanged. The solution for the pivots is exactly the same. We still have a well-defined solution for the same right-hand side. We still have the same column space. And we could look at this more generally for many right-hand sides to demonstrate that. But I just wanted to give a little bit of an example to show what do we really mean that we can delete columns and still get an answer for the right-hand side. It's not exactly the same answer because it's only a unique solution rather than an infinite number of solutions, but they're very closely related. Okay. With all of this, we're now ready to define an approach to find the basis and dimension for our column space. Quite simply, we go through elimination. Once we get to an echelon form, we count the number of pivots. The number of pivots is the dimension of the column space. How do we get a basis for this? We go back to the original matrix, and this is very important that for this column space approach, we go back to the original matrix and select the columns that had the pivots. Those are a basis for the column space. This algorithm is sometimes referred to as the casting out algorithm because we're going to throw away some of the vectors from our original set. And in the same way as with the row space algorithm, we can use this to actually compute the row space or to find a basis for an arbitrary set. We can do the same thing with the casting out algorithm. We start with an arbitrary spanning set. We create a matrix whose columns are that set. Carry out elimination, either just to U or to R. And then the pivot columns from that original matrix are a basis. This is probably best demonstrated again with an example. So let's start first of all just directly computing the column space. Start with this same 4x4 matrix that we looked at for the row space and ask, can we find a basis and dimension of the column space? Start with elimination, upper corner, eliminate downwards to zero out the first row, over and down. We have a 0. We need to do a row exchange because we have non-zeros below. Remaining in this position for a pivot, eliminate downwards to zero out the row below. We move over into the right. Free variable has been identified, no pivot. Move over to our next pivot. This is a upper triangular echelon form. We have 3 pivots. And so the dimension of the column space is 3. How do we get a basis for this column space? Again, very, very important to remember that we go back to the original matrix. The free variable column was the third one, so we remove that column. And the 3 pivot positions, x1, x2, x4, these columns become our basis vectors, 1, 1, 0, 2, 1, 1, 1, 3, and 1, 2, 1, 4. Right? Only tricky piece here is to remember to go back to the original matrix when you're defining the columns. Okay. So let's think about, again, an example where we want to use this approach to find a basis for an arbitrary spanning set. Let's start with this set of vectors defined here. This is the same set of vectors, again, that we did in the second example for the row space algorithm. Here, we start off by generating a matrix whose columns match this, have to orient it appropriately. Right? This is the casting out algorithm. The vectors are in columns. Once we have that in place, we carry through elimination in our standard way. Simply 2 elimination steps gives us an upper triangular form. We can stop. If we're just trying to use this casting out algorithm, we're just trying to find a basis going back to the original matrix, there is no benefit going any further. We've identified our pivot. There's 2 of them, so the dimension is 2. Our free variable is the 3rd column. So how do we find a basis? We go back to the original matrix, delete that free variable column, and we're left with pivots in x1 and x2 column. And these 2 columns are our basis. Now, one of the nice things about this casting out algorithm, and in some applications this is a very helpful feature, is that the basis we get from the casting out algorithm, because we have to move back to the original matrix, the basis is a subset of what we started with. These 2 vectors were part of the original set. What this casting out algorithm has done has identified which vectors from the original set can we get rid of, which vectors are linearly dependent, and we can eliminate them without changing the linear span. This is different than what the row space algorithm does. The row space algorithm gives us a basis, but it doesn't really, the basis we get is changed from the original set. All right. That wraps up our initial discussion of basis and dimension, and our discussion of how we compute basis and dimension with either a row space oriented approach or a column space oriented approach. In the next video, we will extend these ideas to some of the other subspaces of a matrix, the null space, the so-called, and the left null space, and see how all of these 4 subspaces are related to one another, how their dimensions are related to each other, and to the shape of the original matrix. Thank you, and goodbye.